So this relationship is the relationship for the fuel remaining for the number of kilometers traveled for some ship. So always a good point to put into your graph is when the independent variable is equal to 0. So 0 kilometers, my dependent variable is going to be 300 liters. So it looks like we start off with 300 liters of fuel. And as we travel some kilometers, we're going to lose some fuel. So let's say we travel 100 kilometers. Okay, so maybe we should make smaller increments. Let's say 50 kilometers. We're going to lose 25 liters of fuel. Okay, so 0.5 times 50. Okay, subtract that from 300. Okay, we have 100 kilometers traveled. We're going to end up with 250. Okay, so let's go 300. That's going to be 150 kilometers left. And then let's go all the way to 600, and we're down to 0. Okay, so when I graph this then, actually let's just do the relationship. So what's the relationship for this function? In function notation, it's going to be the fuel remaining. So we're going to say f of x is equal to 300 minus 0.5 times the independent variable x, which is the kilometers traveled. What are the x and y intercepts? Well, the x and y intercepts are going to be when x is 0 and when y is 0. These are very useful coordinates to help us graph. So when I draw my graph here, and I know that I can't go less than 0 for either kilometers or fuel, I can say that my x-intercept is 300 kilometers, sorry, 300 liters. Okay, and my y-intercept here is going to be 600 kilometers. Okay, so I'm going to go from negative 100 to, let's say, 700 kilometers, and then negative let's say negative 50 to 350. And again, these are just approximate numbers to give me an idea what this picture is going to look like. And we know that the pattern of this relationship is basically it's just going to go straight down like that. And we have at 50, 300 kilometers, we're going to be right about there. 100 kilometers, 50 kilometers, we're about there. 100, we're about there. And 600, we end up down here. Okay. So again, this is not like a work of art here. We're just getting a general idea of what we're graphing. I also am indicating the domain and range here because I'm stopping the graph at 0 and 0. Okay. So my x-intercept is x equals 600 kilometers. The y-intercept is 300 liters. The domain and range, because of the restriction on this, not the relationship, the equation relationship, but the word problem, the domain is going to be from 0 to, oops, I should state this here. It's going to be from 0 to 600. Okay, and this is a continuous variable, so I'm going to go XER, and my range is going to go from 0 to 300 liters, and again it's a continuous variable, so YER. The ratio of change, which is really important, the ratio of change, some of you may know where to find the ratio of change in the equation, but the ratio of change we can really just find in the table. Okay, so I go plus 50. This is minus 25. Okay, so my ratio of change is going to be negative 25 liters for every 50 kilometers. Okay, and I can simplify that, and I want to make sure that that ratio of change is consistent. Plus 200 kilometers minus 100 liters. Okay, so minus 100 liters. We're always going to compare the y to the x. Okay, and if I simplify this, it's going to be 0.5 liters per 1 kilometer. And that ratio of change is a significant part of the line because remember the line has an angle or slope and position. The angle or slope actually relates to that ratio of change. Okay, and the position is going to relate to the starting amount. So in this case, it'd be $300 is our starting position, and it goes down and this is maybe going to look better this way, it goes down 50 liters for every 100 kilometers, or 0.5 liters per kilometer, okay, as a unit rate.